Hello and welcome to Chapter 14, Solutions Lecture with Foundations of College Chemistry. Let's get right into it. Your outline for this chapter is going to be mainly focused on 4.2, solubility, concentration, 4.4, and then we're going to talk about 4.6, osmosis and osmotic pressure. I'm going to go through the other sections pretty quickly, so if you need to pause the video, feel free. So, general properties of solutions. A solution is a homogeneous mixture of one or more solutes in a solvent. The solute is what's being dissolved, and the solvent is what's doing the dissolving. A lot of times this will be water or an alcohol that is the solvent, and various solutes like salt or another type of alcohol can be dissolved in the solvent. Okay. It's not just always liquids either. Air is a solution that's composed of various different gases. Brass is a solution that in the liquid form is a mixture of various elements to get brass. So don't always think that solutions are just liquids. This is a practice, which soda is a mixture of sugar and water, and really carbon dioxide, the carbonation. Which substance is the solute? So what's being dissolved in the water? Well, we know that the gas is trapped and forced into the water, the CO, sorry, not CO2. It's forced into the water, but doesn't actually dissolve in the water. So if it's primarily sugar and water, what's being dissolved? Well, it's the sugar. Whoops, I apologize. That totally jumped down to the bottom of the lecture. I don't know what I hit there. But what's being dissolved is the sugar. Okay. Here's another practice. Pause the video and try to answer it. And the answer was water. Here are some common types of solutions. Again, you're not going to have to, memorize these, but like I mentioned, brass is a solution, a solid solution. Once it solidifies, it can be in the liquid form as well. Soft drinks, antifreeze, salt water, air are all examples of solutions. These are the properties of a true solution. The biggest thing is that it's homogeneous, okay, and that the solute, whether it be a molecular compound like sugar or an ionic compound like salt, is very, very small. They're transparent, and the solute stays dissolved. It doesn't precipitate out. So if you're putting sugar in water and you're stirring it and it's dissolving, that's a true solution. But there is a thing where you get too much sugar and there's not enough water to continue to dissolve it. Those are the different types of solutions where we have a supersaturated, a saturated, and an unsaturated solution. And then the solute, what's being dissolved, can be separated from the solvent by physical means like evaporation. Typically filtration doesn't work, but chromatography, that kind of stuff. Solubility. Solubility is the amount of solvent in a given amount of or solute in a given amount of solvent. So solubility is what tells you the specific amount of the substance in the solvent at a given temperature. Okay. When two liquids dissolve into each other, it's called miscible. So the picture there is actually showing an immiscible solution where you have oil and water, and oil cannot dissolve into water. Okay, so that's immiscible. Like dissolves like. That's a pretty good statement as far as being true 99% of the time. Polar compounds will dissolve in polar solvents. So water is a polar molecule, okay? because it is polar, it can dissolve so many things. So ethanol, being a type of alcohol that's just also a liquid, can dissolve in water. And then nonpolar dissolves nonpolar solvents. So here we have carbon tetrachloride, which is a liquid, but it can't dissolve in water because it's nonpolar. Just like oil can't dissolve in water. It's a nonpolar compound. So we need a nonpolar solvent to dissolve it. So we have the example of hexane here. So when we have an ionic compound in something, because ionic compounds can dissolve in water because ionic compounds transfer electrons. So they are able to be dissolved by water because that strong dipole moment that water has between its oxygen and its hydrogen. So what happens is that the individual positive and negative ions, cations are positive, anions are negative, they're surrounded and it's kind of picked apart by the water. So you can see the orientation that the water molecules are taking. So the white is the hydrogen, the red is the oxygen. So see how the white is orientated around the green here? That shows that the positive hydrogens are attracted to the negative chlorine and pops it off the solid salt molecule. And then it doesn't really show, oh yeah, right here. So you see the oxygen surrounded by this light gray, or the light gray molecule atom is surrounded by the red. Well, that light gray is the positive sodium. It's also up here at the top. The oxygen, the negative oxygen, is attracted to the positive Na. So it just kind of picks it apart like a puzzle. Now, I talked about solubility before as saturated, unsaturated, and supersaturated. A solubility table at a given temperature tells you if something is unsaturated, saturated, or supersaturated. Saturated and unsaturated will pretty much dissolve in the solvent and have no precipitate. A supersaturated solution will precipitate out if it's jostled or it reaches a certain temperature, and then it immediately, the solute that was dissolved in it precipitates out because you force the solution to take more solute to dissolve than solvent that was available. So solubility increases with temperature for most solids. These are like the hot pink lines. But for some gases and for some hydrochloric acid, for some compounds, solubility will decrease. It doesn't like high temperatures. It won't dissolve as much. So how do we determine unsaturated versus saturated versus supersaturated? Well, that's easy enough. Let's look at KClO3, so potassium chlorate. It starts down here at 0 degrees Celsius at about maybe 3 grams of solute per 100. As we go up to 100 degrees, we can get roughly about 55, 56 grams of solute into the solvent and still have it dissolve. So unsaturated is anything below this line, okay? Anything below this line. So at 100 degrees and 20 grams of potassium chlorate and 100 grams of water is unsaturated. It's way far from the line. Anything on the line, the exact amount on the line, is saturated. And then anything above this line, so at 100 degrees, a supersaturated solution of potassium chlorate in 100 grams of water would be something like 60 grams or 65 or 70. So above the line is supersaturated. On the line, it's saturated. And below the line at a given temperature is unsaturated. At a given temperature for all of those. Okay. All right, so I just went over saturated and unsaturated. The maximum amount of dissolved solute in a solvent is saturated, and it contains less of the maximum amount if it's unsaturated. Supersaturated is more solute than needed to saturate a solution at any given temperature. So how does that happen? Typically heating the solution and then slowly cooling it. The solution can be supersaturated, stay in a liquid form until it becomes unstable. Disturbing it, jostling it in some cases, and you can kind of see this happen. If you put a bottle of water in a freezer and you put it in there and you chill it just for the right amount of time, you can take it out and kind of, smack the side or flick the side, and crystallization will happen. This is kind of a really super simplified way to see what a supersaturated solution looks like. Obviously, water is not a supersaturated solution. There's nothing in it that's dissolved, but it's just to see the crystallization part. A lot of our hot packs or cold packs are supersaturated solutions. The supersaturated solution is typically in like a little vial inside the bag. That's why you have to kind of crack it and then shake it up. Typically cold pack has more of these supersaturated solutions. Hot packs typically work on your body heat, and the substance inside reacts to that heat to make it hotter. But typically cold packs, you have to like break them or pop them. There's a vial inside, and then you shake it up, and then it becomes really cold. All right, so the rate of dissolving solids. So this is like surface area. If I have like a big chunk of sugar, it's going to take a heck of a lot longer for it to dissolve in hot or cold water compared to granulated sugar. So size of the solute does affect how fast it will dissolve. Temperature also affects the rate. You put a cube of sugar in cold water or cold tea versus hot tea, it's going to dissolve faster in the hot tea. So temperature has an effect. And then the effect of solute on concentration. So obviously, the higher the concentration, then the rate is highest at the highest concentration, but it decreases at a lower concentration. So as the solution does approach the saturation point, which is the line, the rate of solute dissolving decreases, which makes sense. It's reaching its maximum amount it can dissolve in a given solvent. Stirring and agitating affects the rate. Obviously, if you stir something, you're breaking up the solvent or the solute in the solvent. You're you're stirring and moving it to allow more surface area, and it increases its solution or its dissolve rate in the solution. So surface area, if you have 6 sides, this gives you kind of a breakdown if you have a small cube versus a huge cube. That's kind of what I was talking about, with the big cube of sugar. If it's little granules of sugars are little cubes, but if I took all that and stuck it in together into one big cube, it's not going to dissolve as fast as it would a bunch of tiny little cubes. Molarity. Molarity is the amount of moles of solute in a liter of solution or solvent. So typically moles per liter. Now the solution is typically it's the mixture of the solute with the solvent, which is typically water or a type of alcohol. So you might see something like 1 with a capital N of KCl. That means 1 mole per 1 liter of KCl, and that's its concentration. Remember, there's 1,000 mils in 1 liter. Okay, so you have to, if you want a certain molarity, you have to get that many moles of that particular substance into 1 liter of solution. So let's talk about how to figure out molarity. Molarity wants you to take if you're given grams of something, to convert that into moles. Then you divide by liters. So here we have 9.35 grams of KCl, that's the solute, and we have 250 milliliters of the solution, which is the water. So first we got to get the grams into moles, and we got to get the milliliters into liters. So we take the given mass of the potassium chloride, and then we multiply it by 1 mole of potassium chloride divided by the mass of potassium chloride. And remember, that's taking the mass of potassium, 39.10, and adding it to the mass of chlorine of 35.45. Once we do that division, we get 0.125 moles of KCl. Then, it doesn't show the math here, but there's 1,000 milliliters in 1 liter. So we just divide 250 by 1,000, and we get 0.250 liters. Then we just divide those two numbers, and we end up with 0.502 moles per liter of calcium chloride, or a 0.5 molar solution. All right, so pause the video. You've got milliliters here. You've got molarity, which is moles over liters, but I want grams, so you're going to have to rearrange this. You have the volume, you have the molarity. I want you to find the grams. So pause the video and see if you can work it out. All right, so if you work that out and got answer D, you were correct. You know the solution volume, you know the solution molarity. Molarity is moles divided by liter. We had this volume, we had the molarity, so we have to rearrange this to where moles of solute is the molarity times the volume. So we take the molarity of 0.45 molarity times the, not milliliters, liters. Liters will cancel, leaving us moles, and then we convert the moles into grams by multiplying by the molar mass of potassium hydroxide. All right, colligative properties of solutions. Some common colligative properties, and it only depends on the number of solute particles, not the nature of the particles, whether big, small, or the solvent. So vapor pressure lowering. Solutions will have a lower vapor pressure than a pure solvent. Boiling point is higher than a pure solvent. And solutions have a lower freezing point than that of the pure solvent. And osmosis and osmotic pressure are colligative properties. So vapor pressure, boiling point, freezing point, and osmosis and osmotic pressure. Now, dissolving a solute in a solvent lowers the vapor pressure of the solvent. As a result, the boiling point is increased while the freezing point is lowered. Now, osmosis. Osmosis is basically the diffusion of water from a dilute or pure water through a semi-permeable membrane into that of a higher concentration. So basically here in the picture, the blue is the water molecules. So up here on the top, we have a very concentrated solution that has sugar in it. So water is going to diffuse up through this membrane to kind of break up the sugar and make it less concentrated. This happens naturally in our cells. When we have too much sugar or too much salt, our cells will take in and release water to balance out the concentration of the different solutes that we have in our body. Osmotic pressure is basically the difference in pressure necessary to stop the flow of water with osmosis and atmospheric pressure. So you've got the sugar solution, it's dipped into a beaker. You've got this semi-permeable membrane here around the bottom of the sugar solution. And then you've got the atmospheric pressure on the outside of the beaker pushing down on the water. So the water will flow through the membrane into the more concentrated sugar solution, causing the solution to rise into the tube. Now, what happens if water goes into the cell too much, too little, or just right? Well, if it's just right, the same concentration in and outside the cell is the same. So it's called isotonic. If water comes out of the cell too much, there's more concentration of sugar or salt inside the cell, then it's called hypertonic. That means that the cell kind of shrinks, it becomes spiky. If water goes into the cell too much and lowers the concentration of solutes inside the cell instead of outside the cell, then it's called hypotonic. So the cell actually swells and becomes bigger. And here are your learning objectives. If you did not understand any of that, make sure you pause the video, backtrack, and redo your notes. And that is the end of Chapter 14. See you in class.